Hello, friends. Welcome back. Or if this is the first time you found your way here, welcome. I'm glad you're here tonight. Before we go any further, did you know that the star keeping you alive right now has a side so violent, so unpredictable, that a single bad day from it could erase every satellite, every power grid, every digital signal on Earth within hours, not in a million years, not in 1,000. It has happened before, and scientists say it will happen again. If you find comfort in these quiet journeys through science and the unknown, you might like to stay a while. You can gently tap the like button. It takes just a moment, and it means more than you know. Subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Now, let's drift. There is a star at the center of everything you have ever known. It rose this morning before you opened your eyes. It warmed the coffee cooling slowly on your table. It pulled at the oceans. It fed the grass. It painted the sky, that particular shade of gold that makes people stop walking and just look up. You have known this star your entire life. And yet, if someone asked you to describe it, really describe it, most people would say the same few things. It's bright, it's warm, it gives us light, it makes things grow, and all of that is true. But here is what most of us were never told. The sun is not a peaceful thing. It is not a lamp hanging quietly in the sky. It is not a steady, reliable fire. It is a churning, roiling, magnetic monster. 1.3 million Earths could fit inside it, and it does not sit still. It explodes, it erupts. It breathes out rivers of charged plasma traveling at 1,000,000 miles per hour. It has moods, if you can call them that, cycles, seasons of fury, and seasons of quiet. And in those seasons of fury, it has changed the course of human history in ways we are only beginning to understand. We have built our entire civilization, our satellites, our power grids, our internet cables, our GPS systems, our financial networks in the shadow of something we never fully respected. We look at the sun every day and we think we know it. We don't. And that more than anything is what tonight is about. Not fear, never fear. This is a story told softly, but it is also a story of one of the most profound blind spots in human history. We have studied the oceans, mapped the continents, decoded the human genome, and somehow, for most of recorded civilization, the thing closest to us, the thing we literally could not survive without, was also the thing we understood the least. Think about that for a moment. The most important object in our solar system in our lives, and for thousands of years, we looked at it and saw only light. There's something almost poetic about that, and maybe a little humbling. Let's go back not 1,000 years, not 1,000,000. Let's go back about 4.5 billion years to a time when the sun didn't exist yet. There was just a vast cold cloud of hydrogen and helium drifting in the darkness between stars. Ancient gas, ancient dust, the remnants of stars that had already lived and died long before our sun was born. Something disturbed that cloud scientists believe it may have been the shock wave from a nearby supernova, a dying star's final explosion, rippling outward through space. And that disturbance set something in motion that would eventually become everything. The cloud began to collapse inward under its own gravity, slowly at first, then faster. As it collapsed, it began to spin, and as it spun, it flattened into a disk. And at the center of that disk, where gravity pulled the hardest and the gas grew densest pressure, and temperature climbed higher and higher and higher until something ignited. Nuclear fusion. Hydrogen atoms squeezed so tightly they could no longer stay apart, began to fuse together into helium. And in that fusion, something extraordinary was released: energy. Not the energy of a match or a furnace or even an atomic bomb. Something on a scale that is genuinely difficult for the human mind to hold. Every single second, the sun converts approximately 600 million tons of hydrogen into helium. Every second. And in that conversion, about 4 million tons of matter is transformed directly into pure energy released as light as heat as radiation. as the solar wind that even now is streaming past your window. 4 million tons of matter gone every second for 4.6 billion years. And yet the sun has barely used a fraction of its fuel. It has another 5 billion years ahead of it. You could spend your whole life trying to understand the scale of that, and you wouldn't quite get there. And that's all right. Some things are meant to be felt rather than measured. Now, here is something that surprises almost everyone when they first hear it: the light touching your skin right now. It is old, far older than you might expect. The energy released when hydrogen fuses in the sun's core doesn't travel straight to the surface. It can't. The interior of the sun is so dense, so incredibly packed with matter, that a photon of light moving at the speed of light can travel only a tiny fraction of an inch before it collides with another particle and is absorbed and re-emitted in a random direction. This process, this stumbling, wandering journey outward through the sun's interior, is called the random walk, and it takes an astonishing amount of time. Depending on which part of the sun a photon starts in, it can take anywhere from 10,000 to 170,000 years for that energy to work its way from the core to the surface. Once it finally escapes into space, it travels the 93 million miles to Earth in just 8 minutes. So, when you step outside on a clear morning and feel the warmth on your face, that warmth has been traveling toward you for longer than modern humans have existed on this planet. It left the core of the sun before our ancestors painted the first images on cave walls, before the woolly mammoth went extinct, before the ice ages came and went. Doesn't that change something just slightly about the way the sunlight feels? The surface of the sun. The part we see, the glowing golden disk, is called the photosphere. It sits at about 10,000 degrees Fahrenheit. That sounds impossibly hot, and it is. But here is one of the sun's great mysteries, one that still keeps solar physicists awake at night. Just above the photosphere, in a region called the corona, the sun's outer atmosphere, the temperature doesn't drop as you move away from the surface. It rises dramatically. The corona reaches temperatures of 1 to 3 million degrees Fahrenheit. Some regions even hotter. That should not be possible. If you move away from a fire, things get cooler. That is how heat works. That is basic physics. And yet here is the sun cheerfully violating our intuitions, getting millions of degrees hotter just a short distance above its own surface. We do not fully understand why. We have theories. Magnetic waves, nanoflares, plasma, instabilities. Scientists are still debating. The European Space Agency's Solar Orbiter mission, launched in 2020, is sending back the closest images of the sun ever captured, and researchers are poring over the data right now, searching for answers. But the corona heating problem, as it's called, remains one of the great unsolved puzzles in astrophysics. And isn't there something wonderful about that? One of the most studied objects in all of human history, and it is still keeping secrets. But the sun's mysteries don't stop at physics. They reach into history, into culture, into the deep, strange story of what it means to be human in a solar system. Every civilization that has ever existed, without a single exception, built something around the sun. The Egyptians mapped its path through the sky with extraordinary precision and built their entire religious cosmology around Ra, the sun god whose daily journey across the sky mirrored the pharaoh's own divine passage through life and death. The Aztecs believed the sun required human blood to keep moving, that without sacrifice it would stop in the sky, and the world would end in darkness. The ancient Pueblo people of the American Southwest built structures aligned so precisely with the solstice sunrise that on one morning each year, a sliver of light enters through a narrow opening and illuminates a spiral carved into stone, a solar calendar that still works perfectly today, nearly 1,000 years later. These were not primitive superstitions. These were sophisticated attempts to understand, to predict, to relate to the most powerful force in their world. They were not wrong to be awed by it. If anything, we might be the ones who've lost something in our age of sunscreen and window blinds and electric light. We've perhaps forgotten what it felt like to truly depend on the sun, to watch it and wonder, to look up and feel small. Here is a question worth sitting with for a moment. When was the last time you actually stopped and looked at a sunset, not photographed it, not glanced at it, but really quietly watched it? The ancients built temples for moments we now scroll past. And here's the other side of that question, the darker one if we barely notice the sun when it's behaving. What happens when it doesn't? Because, and this is where tonight's story begins to open up, in ways you might not expect. The sun has not always been quiet. It has storms. It has cycles of rage and silence. It has reached out across 93 million miles of empty space and touched human civilization in ways that were terrifying, beautiful, and deeply strange. It warped compasses in the 1800s. It disrupted radio signals during World War I. It tripped power grids in Canada in 1989. It lit the skies of Texas and Cuba with auroras so bright that people thought the cities were on fire. It has painted the northern lights over Rome. It knocked satellites out of orbit. And just once in recorded history, it unleashed something so powerful that every telegraph machine in the Western world burst into flames simultaneously without anyone touching them. We are going to explore all of that. The history, the science, the mystery, the things that got the facts wrong and why it matters. The connections between the sun and the human body that science is only recently beginning to map. And finally, quietly at the end of this journey, the sun's ultimate fate and what it tells us about the fragile, extraordinary gift of the moment we're living in right now. But we begin in the simplest possible place, with a man, a telescope, and some spots on the sun that changed everything. In the winter of 1612, a man pointed a telescope at the sun and saw something that would get him into serious trouble, not because what he saw was dangerous, but because what he saw was inconvenient. That man was Galileo Galilei, and what he saw, dark patches drifting slowly across the face of the sun, would ignite one of the earliest and most fascinating scientific controversies in Western history. Because at that time, the dominant view backed by the church and rooted in Aristotelian philosophy held that the heavens were perfect, unchanging, immaculate. The sun, being a celestial body, was supposed to be a flawless sphere of divine light. Dark spots had no place in that picture. Galileo wasn't the first European to notice them. A German astronomer named Christoph Scheiner had observed sunspots around the same time and tried to explain them away as small planets orbiting very close to the sun, just to preserve the idea of a spotless solar surface. Galileo disagreed, publicly. He argued correctly that the spots were on the sun itself, that they moved because the sun rotated, and that their existence proved the heavens were not perfect. They were dynamic, changing, alive. The argument that followed was ugly and political and lasted years. But Galileo was right. What neither of them knew, what no one would know for centuries, was that those quiet dark patches were something far stranger and far more powerful than they appeared. Here is what a sunspot actually is, because this is one of the most common misconceptions in popular science. Most people, if they think about sunspots at all, imagine them as holes in the sun's surface, dark gaps where we're somehow seeing deeper in or cooler regions that are simply less bright. Some people vaguely imagine them as blemishes like age spots on aging skin. None of that is quite right. A sunspot is a region of extraordinarily intense magnetic field. The sun, unlike Earth, is not a solid body. It's a plasma, a superheated gas where electrons have been stripped from atoms, creating a fluid that conducts electricity and generates magnetic fields as it moves. As the sun rotates, and here's the key part, different latitudes rotate at different speeds. The equator rotates faster than the poles. Over time, this differential rotation twists and tangles the sun's magnetic field lines like winding rubber bands around each other until they knot. When a bundle of magnetic field lines becomes strong enough, it can actually suppress the normal convective flow of heat rising from the sun's interior to its surface. The hot plasma that would normally bubble up is held back. And so, that region of the surface becomes cooler than the surrounding area about 6,000 to 7,000 degrees Fahrenheit compared to the roughly 10,000 degrees of the surrounding photosphere. Cooler, yes, but not cool. 7,000 degrees Fahrenheit is still hotter than any fire ever made by human hands. The spot looks dark only by contrast. If you could somehow lift a sunspot out of the sun and place it alone in the night sky, it would shine more brilliantly than the full moon. Darkness here is entirely relative. Now here is where the story deepens, because sunspots don't just sit there looking mysterious. They are part of something larger, something cyclical, something that has been quietly shaping life on Earth in ways that took us embarrassingly long to recognize. In 1843, a German amateur astronomer named Heinrich Schwabe published a paper that had been a decade in the making. For 17 years, he had been recording sunspots almost every day, not to study the sun initially, but because he was actually searching for a hypothetical planet orbiting between Mercury and the sun. He never found the planet, but in all those years of careful daily observation, he noticed something that no one had seen before. The number of sunspots wasn't random. It rose and fell in a regular rhythm roughly every 11 years. Sunspot activity peaked, then declined, then built again to a new peak. This is what we now call the solar cycle, and it matters far more than most people realize. At solar maximum, the peak of activity, the sun's surface is crowded with sunspot groups, some of them larger than the entire Earth. The sun becomes magnetically restless, prone to eruptions and flares. At solar minimum, the surface grows quiet, sometimes days passing, without a single spot visible. And here is something that might genuinely surprise you. The solar cycle affects life on Earth in ways that have nothing to do with the dramatic events like flares and storms. It affects things quieter, subtler, stranger. In the late 1800s, a British economist named William Stanley Jevons proposed something that seemed absurd at the time, that the business cycle, the rhythm of economic boom and bust, was linked to the sunspot cycle. His argument was that sunspot activity affected weather, which affected harvests, which affected grain prices, which rippled through the entire economy. He was mocked thoroughly, and his specific mechanism was indeed too simplistic. But the underlying intuition that the sun cycles could reach down into human economic and social patterns has been quietly vindicated in more sophisticated forms by modern research. Studies published in journals, including Nature and Geophysical Research Letters, have found correlations between solar activity and patterns of drought rainfall and temperature variation effects that are real but subtle, layered beneath the much louder signal of human-caused climate change. The sun doesn't control our climate, but it is one voice in a complex conversation, and we are still learning to hear it. During the years approaching solar maximum, something else happens that affects our daily lives in ways almost no one thinks about. The increased solar radiation, specifically ultraviolet and X-ray emissions, causes Earth's upper atmosphere to expand slightly, puffing outward like bread rising in an oven. And in that expanded upper atmosphere, satellites in low Earth orbit experience more drag. They slow down. Their orbits decay faster. This is not theoretical. In 2022, during a period of elevated solar activity, SpaceX lost 38 of 49 newly launched Starlink satellites because increased atmospheric drag pulled them out of orbit before they could be maneuvered to their operational altitude. 38 satellites gone because the sun was having an active few weeks. Every satellite operator in the world watches the solar cycle the way a ship captain watches the weather. It is operational reality. And then there's the effect on radio communications, something with a long and quietly dramatic history. During solar maximum, the increased ultraviolet radiation from the sun ionizes the upper atmosphere, more intensely changing the way radio waves propagate around the Earth. This can actually improve long-distance shortwave radio communications. Under some conditions, Ham radio operators know this well. And there are communities of radio enthusiasts around the world who plan their international contacts around the solar cycle, waiting for maximum years to attempt the most ambitious long-distance transmissions. But enhanced solar activity can also cause sudden ionospheric disturbances, brief events where a solar flare's radiation reaches Earth in about 8 minutes, disrupting radio communications almost instantaneously. During World War I, military commanders sometimes found their radio communications mysteriously scrambled at critical moments with no enemy interference. It was the sun. It has always been the sun. Here is a question worth pausing on. How many moments in history, how many failed communications, how many unexpected disruptions have had the sun as their silent author, and we simply never knew to look up? Now, let's talk about something that gets surprisingly little attention in popular accounts of sunspots, which is the fascinating and genuinely strange story of what happened when the sun went too quiet. We'll come back to that in a little while. But first, let's look at what sunspots can do when they're not just sitting there looking dark. Because the spots themselves are relatively harmless, they're symptoms, markers, signs that the sun's magnetic field is wound tight, knotted, restless. And when those magnetic field lines eventually snap, when the knots become too tangled to hold the energy releases all at once. The force of that release is something the human mind struggles to picture. An active sunspot group can store energy equivalent to billions of nuclear weapons. Not metaphorically, the numbers when you run them honestly are simply staggering. And when that stored magnetic energy is suddenly released in an event we call a solar flare, it radiates outward across the solar system in a matter of minutes. But here is what's crucial to understand and what most casual accounts get wrong. A solar flare is not the most dangerous thing the sun can do. It's actually the warning shot. The flare is light X-rays, ultraviolet radiation, traveling at the speed of light, reaching Earth in 8 minutes. It disrupts radio communications and satellites, yes, but it passes quickly. What often follows a major flare, not always, but often is something far heavier, far slower, and far more consequential. A coronal mass ejection, ACME. While a flare is light, a CME is matter. Billions of tons of magnetized plasma hurled into space at speeds of 1 to 3,000 kilometers per second. It doesn't travel at the speed of light. It takes anywhere from 1 to 3 days to cross the distance between the sun and Earth, which means, in a way, it gives us a warning. In another way, it means the danger lingers. It builds. It approaches with a kind of slow, inevitable patience that is somehow more unsettling than the instantaneous flash of a flare. And when that wall of magnetized plasma reaches Earth, what it does depends entirely on something that most people have never thought about even once in their lives: the orientation of its magnetic field. Earth has a magnetic field generated by the churning of liquid iron in our planet's outer core. That field deflects most of the solar wind, the constant stream of charged particles from the sun, like a boulder in a river, sending the flow around us rather than through us. It has protected life on this planet for billions of years. Without it, Earth might look more like Mars stripped of its atmosphere, scoured bare. But when a CME arrives, it brings its own magnetic field. And if that field happens to be oriented opposite to Earth's pointing southward, while Earth's points northward, the two fields can connect. They link. And when they link, the CME's energy doesn't flow around Earth anymore. It pours in. The amount of energy that can enter Earth's magnetic system during a major geomagnetic storm is genuinely difficult to hold in the mind. It drives electric currents in the upper atmosphere. It energizes the particles in Earth's radiation belts. It stretches the magnetosphere on the night side of Earth into a long, distorted tail. And it produces the auroras, those shimmering curtains of green and red and violet light that most people associate with quiet beauty in the far north. But the same process that creates auroras also induces electrical currents in anything long and conductive on Earth's surface. Power lines, pipelines, telegraph cables, railroad tracks, and that is where a chapter of history begins. One that changed quietly and permanently the way a small community of scientists thinks about the sun. The solar cycle is not just a number in a textbook, it is a living rhythm. It has been beating since before Earth existed. It shaped the harvests of medieval farmers, the radio silences of World War I, soldiers, the orbital decays of modern satellites. It will shape the lives of people not yet born in ways we cannot fully predict because we are still in the early stages of understanding it. There's something quietly remarkable about that. The most regular, most reliable clock in our solar system, ticking away for billions of years, and we only discovered it in 1843. By accident. By a man who was looking for a planet that didn't exist. Sometimes the most important things are found when you're looking for something else entirely. And now that we've felt the rhythm of the sun's cycles, the quiet build, the magnetic tension, the slow winding of invisible forces, it's time to meet the moment when all of that tension finally broke. The day the sun reached across 93 million miles of space and set the world on fire, literally. On the morning of September 1st, 1859, a young British astronomer named Richard Carrington was doing something he did nearly every clear day, sketching the sun. He had set up a telescope in his private observatory outside London, projecting the sun's image onto a white screen, carefully tracing the positions and shapes of the sunspot groups visible that morning. It was methodical, quiet work, the kind of work that feels important, mostly in retrospect. At 11:18 in the morning, something happened that no human being had ever witnessed before. Two brilliant white patches of light suddenly appeared within a large sunspot group so intensely bright that they outshone the surrounding solar surface by a remarkable degree. Carrington watched stunned as the patches moved and changed shape over the course of about 5 minutes, then faded. He ran to find a witness, came back, and found they had nearly vanished. He wrote up what he had seen. He was careful, appropriately cautious, noting that the connection between what he observed and any effects on Earth was uncertain. He wrote with admirable scientific restraint, "One swallow does not make a summer." 17 hours later, the summer arrived. At approximately 1:44 in the early morning hours of September 2nd, 1859, the largest geomagnetic storm in recorded history swept across Earth. Telegraph systems across North America and Europe, the internet of the 19th century, the communications backbone of the entire industrialized world, failed simultaneously. Some telegraph operators reported receiving electrical shocks from their equipment. Others found that their machines continued to send and receive messages even after being disconnected from their power supplies, running entirely on the electrical currents induced by the geomagnetic storm. In the Rocky Mountains, gold miners were woken in the middle of the night by auroras so bright they thought it was dawn and began making breakfast. In the northeastern United States, people read newspapers by the light of the aurora alone at midnight, without any other illumination. The auroras were visible as far south as Cuba, the Bahamas, Hawaii, and Rome. In Queensland, Australia, people reported being able to see them clearly. This was the Carrington event, and it remains 165 years later the measuring stick against which every solar storm since has been measured. But here is where most popular accounts stop, and where the real story becomes both more interesting and more sobering. In 1859, the world's electrical infrastructure consisted essentially of telegraph wires. Impressive for their time, but limited. The storm fried telegraph systems and caused some fires, but the damage, while dramatic, was contained. Life went on. Farmers farmed. Cities functioned. Most people experienced the Carrington event as nothing more than an unusually spectacular light show in the sky. Now, imagine the same storm arriving this morning. This is not a hypothetical that scientists dismiss as alarmist. A 2013 study commissioned by Lloyd's of London, one of the world's premier insurance markets, a place professionally devoted to calculating real risk, estimated that a Carrington-level event today could cause between 0 trillion and $2. 6 trillion in damages in the United States alone. A 2008 report from the National Academy of Sciences described a worst-case scenario involving widespread long-duration power outages, affecting 130 million Americans, with recovery times not of days or weeks, but potentially of 4 to 10 years. 4 to 10 years without stable electrical power across large regions of North America. Think about what that means quietly without panic, just as a thought experiment. Modern hospitals run on electricity. Water treatment runs on electricity. Food distribution, communication, heating, cooling, financial systems, all of it dependent on a grid that in certain plausible scenarios, a sufficiently powerful geomagnetic storm could compromise in ways that would take years to repair. The transformers that form the backbone of high-voltage power transmission are not like consumer electronics. You cannot simply order a replacement from a warehouse. They are custom-built, extraordinarily heavy, manufactured by a small number of facilities worldwide. And the lead time for a replacement can be a year or more under normal conditions. Normal conditions meaning when only 1 or 2 transformers need replacing at a time, not hundreds simultaneously across multiple continents. This is not science fiction. This is engineering reality. And yet here is something worth pausing on. Genuinely, almost no one thinks about this. Ask 100 people on the street what they fear about space, and they'll mention asteroid impacts, alien invasion, perhaps the eventual death of the sun in 5 billion years. The storm that could actually happen, that has already happened once in recorded history, that researchers estimate has roughly a 12% chance of occurring within the next decade, that one barely registers. A 2019 study published in the journal Space Weather estimated the probability of a Carrington-scale event at between 0.46% and 1.88% per year. That sounds small, but over a decade, those probabilities compound. Over a lifetime, they become surprisingly significant. We insure our cars against accidents. We build seawalls against floods. We have early warning systems for hurricanes. Our preparedness for the most historically documented space weather threat is, to be direct about it, incomplete. Now, to be fair, and this matters, there has been meaningful progress. The National Oceanic and Atmospheric Administration, NASA, and the European Space Agency all operate space weather monitoring and forecasting services. The DSCOVR satellite stationed about 1 million miles from Earth at the gravitational balance point, called L1, continuously monitors the solar wind and provides roughly 15 to 60 minutes of warning before a major CME arrives. Some power grid operators have developed protocols to preemptively take vulnerable components offline during extreme space weather warnings. 15 to 60 minutes. That is the window. For context, a hurricane gives days of warning. An earthquake gives seconds if you're lucky. A major solar storm sits somewhere in between, enough time to take some protective measures, not enough for anything requiring significant lead time. But we've gotten ahead of ourselves slightly because we haven't yet talked about what a solar flare actually does in the minutes and hours before a major CME arrives and why those first 8 minutes matter so much. When a major solar flare erupts its X-ray, an ultraviolet radiation travels at the speed of light and reaches Earth in roughly 8 minutes. In those 8 minutes, it can do something specific and consequential. It can cause what's called a shortwave radio blackout on the sunlit side of Earth, the side facing the sun at the moment of the flare. The mechanism is elegant in a somewhat brutal way. The intense X-ray radiation from the flare ionizes the lower layers of Earth's ionosphere, a region of the atmosphere between about 30 and 50 miles up called the D layer. Normally, the D layer absorbs some radio energy, but during a solar flare, it becomes strongly absorptive, essentially swallowing shortwave radio signals before they can propagate around the Earth. The practical consequences have been documented throughout the 20th century. During the Vietnam War, military planners found that HF radio communications, critical for coordinating operations across vast distances, were occasionally blacked out during solar events at exactly the moments when reliable communication was most needed. Aviation still depends on HF radio for communication over oceanic routes, where satellite coverage can be unreliable and major solar flares can disrupt those communications abruptly and without warning. In July 2012, a massive CME erupted from the sun, one of the largest measured in the modern era. Scientists who have studied the event carefully believe it may have been comparable in strength to the Carrington event. The Earth was not in its path. It passed harmlessly through the region of space our planet had occupied just 9 days earlier. 9 days. That is not a comfortable margin. Now, here's something that almost never gets mentioned in popular accounts, and it's one of the aspects of solar flares I find most quietly remarkable. The light we see during a solar flare, the visible brightening of the solar surface, represents only a fraction of the total energy released. Much of it goes into accelerating particles to enormous speeds. Protons, primarily hydrogen nuclei stripped bare, can be accelerated by the shock wave of a major flare, or CME, to velocities approaching the speed of light. These are called solar energetic particles, or SEPs, and they can reach Earth in as little as 20 to 30 minutes after a major event. For astronauts in space, these particles are a serious radiation hazard. During an Apollo mission in 1972, a major SEP event occurred between the Apollo 16 and Apollo 17 missions, meaning both crews had already returned safely to Earth. Had it occurred during a lunar transit, the radiation exposure for the crew would have been severe and potentially fatal. The Apollo program, by some assessments, was fortunate in ways that were not fully appreciated at the time. Every crewed mission beyond Earth's protective magnetosphere, future lunar bases, potential Mars missions, will need to grapple with this reality. The sun does not care about mission timelines. And there's another layer here, a human layer, that I want to linger on for a moment. When we talk about these events, the Carrington event, the 1989 Quebec storm, the near miss of 2012, we talk about them in terms of infrastructure and economics and risk probabilities. And that framing is important, but it can also make the whole thing feel abstract, remote, like a problem for engineers and policymakers. But the 1989 Quebec blackout wasn't abstract to the 6 million people who spent 9 hours without electricity in a Canadian winter. It wasn't abstract to the patients in hospitals, the families in cold apartments, the drivers on suddenly dark roads. The storm that caused all of that wasn't a Carrington-level event. It was a moderate solar storm, significant but not extreme. What makes the sun's invisible wounds so peculiar is their indifference. There is no malice in a solar flare. There is no targeting. It is simply energy released by physics traveling through empty space, arriving on whatever happens to be in its path. The same process that paints auroras across the sky can, at sufficient intensity, cripple the systems modern life depends on. Beauty and danger woven from the same source. Here is something to sit with every time you've looked up and seen a particularly vivid sunset, those deep reds and oranges that spread across the whole western sky. One of the contributing factors is often elevated particulate activity in the upper atmosphere. Sometimes subtly, the sun itself has had a hand in painting that sky. The same energetic processes that we worry about at their extremes contribute at quieter levels to some of the most beautiful moments in ordinary life. The sun doesn't announce its moods. It doesn't send warnings in forms we naturally recognize. It flares and erupts and breathes out storms, and we either have instruments pointed at it or we don't. For most of human history, we didn't. The Carrington event was documented only because Richard Carrington happened to be sketching sunspots that particular morning, and even then the connection between what he saw and what happened 17 hours later was not universally accepted for years. We have better instruments now. We have satellites and monitoring networks and forecasting models. We are genuinely better prepared than we were even 20 years ago. But the fundamental relationship remains what it has always been: a small, wet, electromagnetically fragile planet, orbiting in the weather zone of a star that operates on its own schedule by its own rules with its own quiet power. And that star does not just reach us through flares and storms. It reaches us more constantly, more gently, in a way that surrounds us so completely. We have learned not to notice it at all, a wind that never stops blowing, from a source that never stops breathing. That is what we follow next. The sun's breath itself, streaming outward in all directions, shaping everything it touches, connecting the sun to the farthest edges of our solar system in one continuous invisible river. Every second of every day, without pause, without rest, the sun is dying a little. Not in the way stars eventually die, not yet, not for billions of years. But right now, at this moment, as you listen to these words, the sun is losing mass, shedding itself, breathing outward in all directions, at once releasing a continuous stream of charged particles, electrons and protons, and heavier ions that flows outward through the solar system at speeds between 250 and 800 kilometers per second. This is the solar wind, and almost no one thinks about it, even though it is one of the most consequential phenomena in the entire solar system. Even though it is in a very real sense the medium through which the sun extends its influence to every planet, every moon, every comet, every spacecraft, every corner of the space between here and the stars. You are right now inside the sun's atmosphere. We all are. The solar wind doesn't stop at some convenient boundary near Earth. It flows past us, past Mars, past Jupiter and Saturn, and the ice giants all the way out to a boundary called the heliopause, roughly 120 times the distance from the Earth to the Sun, where it finally meets the interstellar medium and slows to a stop. The entire solar system, every planet included, sits inside a bubble blown by the sun's own breath. That image stayed with me the first time I really understood it. We think of space as emptiness, cold, still, silent. But the space between planets is not empty. It is filled constantly dynamically with the sun's exhale material, flowing and gusting and spiraling outward in patterns shaped by the sun's rotation. And the story of how we came to understand this is quietly one of the most human stories in the history of science. In 1958, a young physicist at the University of Chicago named Eugene Parker submitted a paper to the Astrophysical Journal. He had done the mathematics carefully, patiently, and his mathematics told him something that essentially no one in the scientific establishment was prepared to accept. Parker calculated that the sun's corona, that mysteriously superheated outer atmosphere we touched on earlier, could not be in static equilibrium. The gas was too hot, moving too fast, subject to pressures that would inevitably drive it outward in a continuous supersonic flow. The sun, he argued, must be continuously shedding material into space. He called it the solar wind. The two reviewers who evaluated his paper rejected it. Their criticism was blunt. Parker's idea contradicted the consensus view that interplanetary space was essentially a vacuum, disturbed only occasionally by specific events like flares. The continuous wind was considered implausible. The journal's editor, Subramanian Chandrasekhar himself, a Nobel Prize-winning astrophysicist, made an unusual decision. He read the paper himself, found no mathematical errors, and published it over the reviewers' objections. 3 years later, in 1962, NASA's Mariner 2 spacecraft, the first successful interplanetary mission, flew past Venus and confirmed with direct measurements exactly what Parker had predicted. The solar wind was real, continuous, and remarkably close to his theoretical values. Eugene Parker lived to see his vindication fully complete. In 2018, NASA launched the Parker Solar Probe, the fastest human-made object ever built, named in his honor while he was still alive, a distinction almost without precedent in the history of the space program. Parker attended the launch at the age of 91, watching the spacecraft that bore his name accelerate toward the star he had spent his career studying. He died in 2022 at 94. The probe named for him continues to spiral closer to the sun, breaking its own speed records with each orbit sending back data from regions of the solar atmosphere no instrument has ever reached before. There is something quietly moving about that. A man proposes an idea. The establishment rejects it. The universe confirms it. And 60 years later, humanity sends a spacecraft into the sun's corona, in his name still learning from the foundation he built. Science at its best works this way. Slowly, correctively, beautifully. Now, let's talk about what the solar wind actually does, because its effects are stranger and more far-reaching than most people realize. The most visually dramatic effect, the one that has inspired art and mythology and wonder across centuries, is the aurora. We touched on the mechanism briefly in the context of geomagnetic storms, but the aurora in its quieter daily form is worth understanding on its own terms, because the common explanation most people have heard is subtly but importantly wrong. Most people, if asked how auroras form, will say something like, the solar wind hits the atmosphere and makes it glow. That's not quite right, and the correct version is actually more interesting. The solar wind doesn't directly strike Earth's atmosphere. Earth's magnetic field deflects the vast majority of it, sending it flowing around the planet. What actually happens is more subtle. Some of the solar wind's charged particles get funneled along Earth's magnetic field lines toward the polar regions, the areas where the field lines converge and dip toward the surface. There they collide with atoms and molecules of oxygen and nitrogen in the upper atmosphere, exciting those atoms to higher energy states. When the atoms return to their normal state, they release that energy as light. The colors are determined by which atoms are involved and at what altitude. Oxygen at high altitudes around 200 miles up produces rare red auroras. Oxygen at lower altitudes produces the most familiar green. Nitrogen contributes blues and purples. Each color is a chemical signature, a readable record of what the solar wind is doing to our atmosphere at that moment. Here is something that surprises almost everyone. Auroras don't only happen on Earth. They happen on every planet in the solar system with a magnetic field. Jupiter has the largest and most powerful auroras in the solar system. The Hubble Space Telescope has photographed them, repeatedly glowing rings around Jupiter's poles that dwarf anything seen on Earth. Saturn has them. Uranus and Neptune have them. Even some of Jupiter's moons, Ganymede, which has its own magnetic field, produce miniature auroral displays. The solar wind writes the same message in light across the entire solar system. The specific words differ by planet, by magnetic field, strength by atmospheric composition. But the author is always the same. And the solar wind does something else, something that took scientists much longer to appreciate and which has implications that are still being worked out. It sculpts comets. Every comet has two tails. Most people know this, but few know why. One tail. The dust tail curves gently behind the comet along its orbital path, formed by the pressure of sunlight, pushing dust particles away from the nucleus. This tail always curves slightly backward along the orbit, like the wake of a boat. The second tail, the ion tail sometimes called the plasma tail, does something different. It always points directly away from the sun, regardless of which direction the comet is moving. Always, precisely. Even when the comet is moving toward the sun, the ion tail streams out behind it, pointing away from the sun, not behind the direction of travel. This puzzled astronomers for a long time. In the 1950s, the German astronomer Ludwig Biermann studied comet tail orientations and concluded that the only explanation was a continuous stream of particles flowing outward from the sun, particles with enough force to push ionized gas directly away from the sun, regardless of the comet's motion. He proposed the existence of the solar wind on this basis actually a few years before Parker developed his theoretical framework. Every comet that has ever appeared in human skies, every comet that ancient astronomers watched and wondered about, every comet that inspired fear and prophecy and myth, was demonstrating the solar wind's existence. The evidence was there painted across the sky in two distinct tails for as long as humans had been looking up. We just didn't know what we were seeing. That happens more than we might like to admit. The universe is patient about revealing its workings. It leaves evidence everywhere. We find it when we're ready. Now the solar wind's interaction with Earth is not only a matter of auroras and particle physics. There is a more intimate connection, one that touches the question of why Earth is habitable at all, and why Mars, which once may have been far more Earth-like, became the cold, thin-air desert it is today. Earth's magnetic field, the magnetosphere, is not just beautiful in the way it generates auroras. It is existentially important. The solar wind over long time scales is capable of stripping away planetary atmospheres. The process is called atmospheric escape, or atmospheric sputtering. Solar wind particles collide with atmospheric molecules near the tops of atmospheres and can transfer enough energy to knock those molecules into space permanently. On Earth, the magnetosphere deflects most of the solar wind before it can reach the upper atmosphere, protecting the atmosphere from this gradual erosion. Mars has no global magnetic field. It lost it approximately 4 billion years ago, for reasons scientists are still investigating. With the shield gone, the solar wind began to strip Mars's once thicker atmosphere molecule by molecule over hundreds of millions of years. NASA's MAVEN mission, which began orbiting Mars in 2014, has directly measured this process. Happening in real time, the solar wind is still stripping about 100 grams of Martian atmosphere into space every second. 100 grams per second. Continuous. For billions of years. That is where Mars's water went, not underground, not locked in ice entirely, but largely lost to space along with the atmosphere that once held it liquid. The solar wind didn't just change Mars's weather, it changed what Mars fundamentally is, and Earth could have gone the same way. The same process that turned Mars into a desert was aimed at Earth too. The crucial difference is that ancient Earth maintained its magnetic field generated and sustained by the liquid iron churning in its outer core, kept molten by heat from the planet's formation, and from radioactive decay in its interior. Earth's habitability is in part a story about the planet's interior, keeping the lights on against the sun's persistent erosion. Our magnetic field is not a given. It is a geological achievement maintained by processes deep beneath our feet that we have benefited from for our entire existence without ever thinking about it. Here is a question worth sitting with gently. If you had to identify the single most important invisible shield in human history, the one that made all of life on Earth possible, most people would never think to name the magnetosphere. And yet, there it is. The solar wind has one more dimension worth exploring before we move on, and it's perhaps the most counterintuitive of all. The solar wind doesn't just carry particles. It carries the sun's magnetic field stretched outward, wound into a spiral shape by the sun's rotation, forming a vast structure called the heliospheric current sheet. This is the largest structure in the solar system, a curved, rippling surface that extends from the sun all the way to the heliopause, separating regions of the solar wind with opposite magnetic orientations. Earth crosses back and forth through this current sheet as it orbits the sun, roughly every week, depending on the sheet's orientation. Each crossing can trigger minor geomagnetic disturbances, small but measurable fluctuations in Earth's magnetic field. These are generally not large enough to cause problems, but they are a reminder that the sun's influence is not just occasional, it is structural, woven into the fabric of the space Earth moves through. When Voyager 1 crossed the heliopause in 2012 and entered true interstellar space, it didn't find silence. It found a change. The solar wind's influence ended, the interstellar medium's influence began, and the instruments on a spacecraft launched in 1977, running on the last reserves of its nuclear power supply, sent back measurements that scientists compared to the crossing of a shoreline. Here, the sun ends. Beyond this other stars, the solar wind defines the boundary of the sun's dominion. Everything inside that boundary, every planet, every moon, every asteroid, Every human spacecraft ever launched exists within the sun's breath. We live inside a star's exhalation. That is not a metaphor. It is a measured, confirmed physical reality. And if the sun's breath shapes the space around us so completely, you might find yourself wondering what the sun looks like up close. Not from 93 million miles away. Closer, much closer. Because it turns out that when you get near enough to actually observe the sun's surface in detail, you find something that weather forecasters on Earth would recognize immediately, even if the scales are almost beyond imagining. Something that rains, something that storms, something that has its own seasons and its own tides and its own rhythms of calm and fury, a full weather system operating on the surface of a star. There is weather on the sun, not weather the way we experience it, not clouds building over mountains, not humidity rising from warm oceans, not the particular smell of rain approaching across a dry field, but weather nonetheless, storms and calms, flows and disruptions, patterns that build peak and dissolve, a full meteorology operating on a scale that makes Earth's most powerful hurricanes look like ripples in a teacup. And one of the strangest, most visually stunning phenomena in all of solar science is something that most people have never heard of, something that, when you first see imagery of it, looks so wrong, so counterintuitive that the mind briefly refuses to accept what the eyes are showing. It rains on the sun, not water, nothing so gentle. What falls is plasma, superheated, magnetized plasma, cooling relative to its surroundings, losing its buoyancy and cascading back down along magnetic field lines and drains and rivers and streams that dwarf entire planets. Each droplet of this coronal rain, if you can call something larger than a mountain range, a droplet falls at speeds of hundreds of kilometers per second, tracing the invisible architecture of the sun's magnetic field as it descends. The first time I encountered imagery of coronal rain, captured by NASA's Solar Dynamics Observatory, I had to watch it several times before I could properly orient myself to the scale. What looked like delicate threads of luminous material flowing downward were structures hundreds of miles wide, falling across distances larger than the diameter of Earth. The sun was raining on itself, and it was beautiful in a way that felt almost designed, almost intentional, even though it is of course pure physics. Let's understand how this happens, because the mechanism reveals something profound about the way the sun works. The sun's corona, that mysteriously superheated outer atmosphere, is threaded throughout with magnetic field lines that arc upward from the surface in enormous loops. These loops, called coronal loops, are not uniform. They vary enormously in size, temperature, and density. Some are compact and hot and bright. Others are vast, cooler, and filled with plasma that is in a constant state of dynamic tension between the heat driving it upward and the gravity pulling it down. In certain conditions, particularly when a coronal loop is heated unevenly, or when the plasma within it cools faster than the surrounding material, a thermal instability sets in. The cooler, denser plasma loses buoyancy. Normally, hot plasma in the corona is supported partly by its own thermal pressure pushing outward against gravity. But when it cools, even relatively, even to temperatures still measured in tens of thousands of degrees, it becomes heavier than the surrounding material, and it falls. It falls along the magnetic field lines, not straight down the way rain falls on Earth, pulled purely by gravity toward the ground. Instead, it follows the curves of the magnetic loops, sometimes falling in graceful arcs, sometimes in nearly vertical sheets, sometimes in spiraling threads that trace the helical structure of twisted magnetic fields. The magnetic geometry of the sun determines the path of its rain the way riverbeds determine the path of water on Earth. In 2012, astronomers using the Solar Dynamics Observatory published the first detailed observations of coronal rain and described it as one of the most visually striking phenomena they had ever seen in solar imagery. One researcher described watching a prominence, a large arch of plasma extending above the solar surface, erupt partially and then rain back down on itself, the falling material illuminating the magnetic structure of the corona in a way that had never been seen before. Here is something genuinely surprising about all of this. Coronal rain may actually help explain the corona heating problem, that unsolved mystery from part 1. The question of why the sun's outer atmosphere is millions of degrees hotter than its surface. One of the leading theories involves a process called chromospheric evaporation and condensation cycling. In this model, energy deposited at the base of coronal loops heats the plasma, which rises into the corona. As it cools and condenses high in the corona, it falls back as coronal rain, releasing energy as it descends, and the cycle repeats. The rain is not just a consequence of the corona's behavior, it may be part of the engine that drives it. We are still learning. The Parker Solar Probe and the Solar Orbiter mission are sending back data from closer to the sun than any previous instruments, and researchers are working to understand whether the rain cycling mechanism plays a significant role in maintaining coronal temperatures. The question is open, the investigation is active, and that is in its own quiet way exciting. But coronal rain is only one feature of the sun's complex surface weather. Let's widen the view. The sun's visible surface, the photosphere, is covered in a pattern called granulation. Each granule is a convection cell where hot plasma rises from below, spreads outward, cools slightly, and sinks back down at the edges. These granules are typically about 600 to 1,000 miles across, roughly the size of Texas, and they live for about 8 to 20 minutes before dissolving and being replaced by new ones. The entire solar surface is covered in millions of them at any given moment, giving the sun a texture like the surface of a very hot, very large orange. But granulation is only the smallest scale of convection visible on the sun. Above it sits a phenomenon called supergranulation cells, roughly 20 to 30 times larger than individual granules, lasting for days rather than minutes, whose origins and driving mechanisms are still not fully understood. And above that, there may be an even larger scale of convection, called giant cells, theoretically predicted to be hundreds of thousands of miles across, whose existence has been debated for decades. Some observations suggest they are there. Others suggest they are much weaker than models predict. The sun's weather system has layers within layers operating at different scales, interacting with each other in ways that supercomputers are still struggling to model accurately. This matters beyond pure scientific curiosity. The interaction between these different scales of convection and the sun's magnetic field drives the solar cycle itself, the 11-year rhythm of sunspot activity we explored earlier. Understanding convection is not separate from understanding the cycle. They are the same system looked at from different angles. Now there is another dimension of solar weather that receives very little attention outside specialist circles, and which I find deeply interesting precisely because of its implications for how we think about prediction and forecasting. The sun has something analogous to weather forecasting. It is called space weather forecasting, and it is practiced by agencies including NOAA's Space Weather Prediction Center and the European Space Agency's Space Weather Service. Forecasters there monitor the sun, continuously watch for developing active regions, assess the likelihood of flares and CMEs, and issue warnings and alerts, just like meteorologists watching a storm system developing over the Pacific. But here is where the analogy breaks down in an instructive way. Earth's weather, for all its complexity, operates in a fluid, the atmosphere whose behavior is governed by equations we understand reasonably well. We have dense networks of sensors on the ground, in the air, on the oceans, and in orbit. We have decades of historical data. And still beyond about 5 to 7 days weather, forecasting loses predictive power. Rapidly, the system is simply too chaotic. Solar weather forecasting faces all of those challenges plus several additional ones. The sun's interior is largely opaque to direct observation. We cannot see what is happening beneath the photosphere, the way we can observe atmospheric dynamics on Earth. We have far fewer measuring points, essentially a handful of spacecraft, rather than thousands of ground stations. and the physical processes involved magnetohydrodynamics, plasma, physics, nuclear reactions, are in many ways less well characterized than atmospheric fluid dynamics. The result is that space weather forecasting is, at present, roughly where terrestrial weather forecasting was in the 1960s. We can recognize patterns. We can identify active regions likely to produce flares. We can sometimes estimate the probability of a major event in the next 24 to 48 hours. But specific prediction this active region will produce an X-class flare at this specific time remains largely beyond current capability. That gap between what we need to know and what we currently can know is not a comfortable one, given the stakes. A 2021 report from the Space Weather Advisory Group to the White House noted that improving space weather forecasting is a national security and infrastructure priority. The report called for expanded monitoring, improved modeling, and importantly, better placement of monitoring spacecraft to give earlier warning of incoming CMEs. Currently, our primary space weather monitor, the DSCO VR satellite at L1, gives us 15 to 60 minutes of warning before a CME arrives. Scientists have proposed placing additional monitoring spacecraft at L4 and L5 gravitational balance points that flank the Earth in its orbit, which would provide a three-dimensional view of the space between Earth and the Sun, and could potentially extend warning times significantly. Those spacecraft have not yet been built. There is a pattern here worth naming explicitly, because it appears throughout the history of our relationship with the Sun. We understand the risk, we can articulate what it would take to reduce it, and we proceed at a pace that is, let's say, unhurried. Part of this is economic space. Weather preparedness competes for funding with many other priorities. Part of it is the familiar human tendency to underweight low-probability, high-consequence events, especially when they feel abstract and remote. But here is something that reframes that abstraction, and it's worth sitting with for a moment. The Sun's weather doesn't only express itself in dramatic, civilization-disrupting ways. It expresses itself in daily, ordinary, quietly consequential ways that touch almost every technology modern life depends on. GPS accuracy fluctuates with solar activity. The same ionospheric disturbances that affect radio communications can introduce errors into GPS positioning that matter enormously for precision agriculture, aviation, navigation, and autonomous vehicle systems. The drag on satellites changes with the solar cycle, requiring continuous orbit correction burns that consume fuel and shorten satellite lifespans. Even the timing signals used by financial networks to synchronize global transactions can be affected by major space weather events. The Sun's weather is not something that happens elsewhere to other people at dramatic historical moments. It is happening now, continuously touching systems you interact with every day in ways so subtle they are invisible until they aren't. Ask yourself this when your GPS briefly gives you a wrong turn, or your phone signal drops inexplicably on a clear day, or a satellite image looks slightly blurred. How often does the Sun enter your thinking as a possible cause? Probably never. And yet, for engineers and operators who maintain these systems, the Sun is a constant operational reality, a background factor in every calculation. There is one more aspect of solar weather I want to explore before we leave this subject, because it connects the Sun's surface behavior to something ancient and personal and strange. In 2003, a series of solar flares and CMEs, now called the Halloween storms, produced the most intense space weather of the modern satellite era. Auroras were seen as far south as Texas and Florida. Multiple satellites suffered permanent damage or were temporarily disabled. The Martian radiation monitors on board NASA's Mars Odyssey spacecraft were so overwhelmed by energetic particles that one instrument was permanently damaged. Airlines rerouted polar flights to avoid radiation exposure. The International Space Station crew took shelter in the most shielded part of the station for extended periods. And yet, and this is the remarkable part most people on Earth experience that week as entirely ordinary, the sun rose and set. The skies were clear or cloudy as they always are. The world went about its business. The most intense space weather in decades was happening all around them invisible, conducting its intricate and consequential business in the sky above, while the daily human world continued completely unaware. The sun's weather and our weather occupy the same sky. But for most of history, and for most people even now, they might as well be in different universes. That gap between what is happening and what we perceive is one of the recurring themes of tonight's journey, and it appears again perhaps most dramatically in a chapter of the story that reaches not into the sky above us, but into the soil beneath our feet, into the wood of ancient trees, into layers of ice laid down centuries before any living person was born. Because it turns out that Earth itself has been keeping records of the sun's behavior for far longer than any human instrument, any telescope, any spacecraft. The planet we live on has been quietly archiving the sun's entire modern history in a language we only recently learned to read. Somewhere in northern Scandinavia, there is a pine tree that has been alive for more than 9,500 years. It is not tall or impressive looking. The harsh Arctic conditions have kept it small, gnarled, close to the ground. But inside its wood, laid down ring by ring across nearly 10 millennia, is a continuous record, a diary written in carbon and cellulose, a document that no human hand composed, but that human minds have learned painstakingly to read. And what it tells us about the sun is something no telescope, no spacecraft, no observatory could have revealed on its own. This is the story of how Earth became the sun's own archive, and how scientists learned to decode a message that has been written in wood and ice and stone since long before any civilization existed to wonder about the sky. Every year, a living tree adds a new ring of growth. In good years, warm, wet, long-growing season years, the ring is wide. In poor years, narrow. Dendrochronology. The science of reading tree rings has been used for decades to reconstruct past climates, date ancient structures, and understand the rhythms of ecological history. But there is something else hidden in those rings, something far more subtle that became one of the most powerful tools in solar science: carbon-14. Carbon-14 is a radioactive isotope of carbon produced in Earth's upper atmosphere when cosmic rays, high-energy particles from space, collide with nitrogen atoms. This carbon-14 gets incorporated into carbon dioxide, which gets absorbed by plants during photosynthesis, which gets built into the structure of wood. Every ring in every tree contains a record of how much carbon-14 was in the atmosphere during the year that ring formed. And here is the connection to the sun. The sun's magnetic field, carried outward by the solar wind, acts as a partial shield against cosmic rays entering the solar system. When the sun is active magnetic field, strong solar wind, dense fewer cosmic rays penetrate to Earth's atmosphere, and less carbon-14 is produced. When the sun is quiet, magnetic field, weak solar wind, sparse more cosmic rays get through, and carbon-14 production increases. By measuring carbon-14 levels in tree rings across thousands of years of continuous record, built from overlapping sequences of living and dead ancient trees, scientists can reconstruct the history of solar activity going back more than 10,000 years. Read that number again. 10,000 years. The entire span of human civilization, from the first cities of Mesopotamia to the present moment and beyond. All of it archived in the chemistry of wood. The picture that emerges from this archive is one of a sun that has always been variable, sometimes more active, sometimes less cycling, through its familiar 11-year rhythm, but also showing longer patterns of rising and falling activity over centuries. Solar physicists call these longer patterns grand solar minima and grand solar maxima, extended periods when the average level of solar activity is lower or higher than usual. And embedded in that long record is a signal so sharp, so anomalous, so unlike anything around it that when researchers first saw it, they had to check their data multiple times before accepting what it meant. In 2012, a Japanese researcher named Fusa Miyake was analyzing carbon-14 levels in ancient Japanese cedar trees when she found something extraordinary. In the rings corresponding to 774 and 775 AD, a 2-year period during the reign of the Tang dynasty in China and the early reign of Charlemagne in Europe, carbon-14 levels suddenly spiked by approximately 1.2%. A 1.2% spike sounds modest until you understand the baseline variability. Normal year-to-year fluctuations are a fraction of that. This spike was roughly 20 times larger than anything seen in the surrounding centuries. Something had happened to Earth's atmosphere in 774 and 775 AD. Something that flooded the upper atmosphere with an extraordinary pulse of high-energy particles. Something big enough to leave a mark that is still readable in the wood of trees more than 12 centuries later. What was it? The initial candidate was a supernova, an exploding star relatively nearby in the galaxy. But historical records from that era, while limited, contain no accounts of a new bright star appearing in the sky that year, which a nearby supernova almost certainly would have produced. Chinese astronomers in the Tang court were diligent sky watchers, and they recorded nothing of the kind. The next candidate was a gamma ray burst an incredibly powerful explosion from a distant collapsing star. But calculations showed that a gamma ray burst capable of producing this signal would have needed to be so close and so powerful that Earth would have suffered dramatic and lasting damage to its ozone layer, with measurable consequences for life. No such consequences are visible in the biological record. The conclusion that has gained the most support, supported by follow-up analyses of tree ring records from trees across multiple continents, all showing the same spike at the same time, is that the 774 to 775 event was caused by an extreme solar particle event, a solar storm so powerful so far beyond anything in the modern instrumental record that it dwarfs even the Carrington event of 1859 in terms of energetic particle output. Some estimates suggest the 774 to 775 event may have been 10 to 100 times more energetic than the Carrington event. Let that number settle for a moment. The Carrington event, the storm that set telegraph wires on fire that produced auroras visible from Cuba, was by this analysis not even close to the sun's worst behavior within historical times. Not even close, and nobody knew it happened. Not the Tang dynasty astronomers, not Charlemagne's scribes, not the monks copying manuscripts in Irish monasteries. Not a single human record from 774 AD mentions anything unusual in the sky. An event potentially 100 times more powerful than the greatest solar storm of the modern era, passed through the solar system and was absorbed into the Earth so quietly that it left no trace in human memory, only in the slow, patient chemistry of wood. Since Miyake's original discovery, researchers have found additional carbon-14 spikes in the tree ring record. Another major event occurred around 993 to 994 AD. A smaller but still significant event around 660 BC. Researchers are actively searching for others, building a catalog of extreme solar events that extends human awareness of the sun's behavior back through millennia. This work has a direct practical implication that is not comfortable to sit with the 200 years of telescopic solar observation we have accumulated since Galileo. The modern instrumental record we use to assess solar hazard may be deeply unrepresentative of what the sun is actually capable of. We have been measuring a small, perhaps unusually quiet slice of solar history and using it to estimate risk. It is in a way like trying to assess earthquake hazard in a region by studying only the last 2 centuries of records without knowing that the really large earthquakes in that region happen every 1,000 years. The ice cores add another layer to this picture, and they are worth exploring on their own terms, because the information they preserve is different in kind from what trees record. Deep in the ice sheets of Greenland and Antarctica, snow has been accumulating for hundreds of thousands of years. Each year's snowfall compresses into a layer of ice, trapping within it tiny bubbles of the ancient atmosphere, dust particles, volcanic ash, and crucially for solar science, trace chemicals including nitrates and beryllium 10. Beryllium 10, like carbon 14, is produced by cosmic ray interactions with the atmosphere. It falls out of the atmosphere and gets deposited in snow, where it is preserved in ice layers. By drilling ice cores and measuring beryllium 10 concentrations layer by layer, scientists can reconstruct cosmic ray intensity and therefore solar activity going back hundreds of thousands of years. The European Project for Ice Coring in Antarctica, known as EPICA, has drilled ice cores preserving a climate and solar activity record extending back approximately 800,000 years. 800,000 years, long before anatomically modern humans existed, long before our species had spread across Africa. Back to a time when our distant ancestors were learning to control fire, and the ice above Greenland was already quietly recording the sun's behavior year by year, snowflake by snowflake. The picture from ice cores is consistent with what trees tell us about more recent millennia, but richer in long-term context. The sun has been cycling through periods of higher and lower activity on multiple timescales. The 11-year sunspot cycle, longer grand cycles of perhaps 80 to 100 years, called Gleisberg cycles, and even longer patterns spanning centuries. The sun is not erratic. It has rhythms nested within rhythms like harmonics in a musical chord. We are learning to hear the chord. There is one more archive worth mentioning, because it is perhaps the most poignant of all, and because it connects the abstract world of solar physics to something viscerally human. In 1006 AD, a supernova exploded in the constellation Lupus, the brightest stellar event in recorded history, visible in daylight for weeks, bright enough to cast shadows at night. It was recorded by astronomers in China, Egypt, Iraq, Switzerland, and Japan. That event is not solar, of course, but the diligence with which ancient observers recorded it, the detailed accounts left by medieval astronomers who understood they were seeing something extraordinary, stands in interesting contrast to the apparent silence around the 774 to 775 solar event that was by physical measures potentially far more energetic. The supernova was visible, the solar particle event was not. This is a recurring theme in our relationship with the sun's behavior. The most dangerous things it does are often the least visible. The most consequential events leave no aurora, no flash, no sign that the human eye can register. They happen in wavelengths we cannot see, in particle energies we cannot feel, in magnetic fields we cannot sense. They are recorded in the bodies of trees and the layers of ice-patient non-judgmental archives that simply record what happened, without drama, without emphasis, without any indication that what they are preserving might matter enormously to small biological creatures who would evolve millennia later to read their pages. Here is a question that seems simple but opens into something genuinely deep. How much of the past do we actually know, and how much have we been reconstructing from proxies from shadows of events cast in chemistry and biology rather than from direct human observation? Most of human history has been lived through astronomical events, solar storms, cosmic ray fluctuations, long cycles of solar activity that simply had no place in the conceptual frameworks available to the people living through them. Not because those people were less intelligent, because the instruments didn't exist, because the concepts hadn't been developed, because the connection between a carbon atom in a tree ring and a charged particle ejected from the sun's corona is not an obvious one, and working it out required centuries of accumulated science across physics, chemistry, biology, and astronomy. We are the first generation in human history with the tools to read the sun's ancient record in any detail. And what that record tells us about variability, about extremes, about the gap between modern experience and the full range of solar behavior is still being digested. The trees have been waiting patiently for us to ask the right questions. The ice has been preserving its answers for longer than our species has existed. And what the record shows above all is that we think we know the sun of the last 200 years of careful observation, is only one face of something far older, far more variable, and far more powerful than our modern experience has shown us. But there is one period in that long record that stands apart from all the others, not because of a sudden spike in carbon-14 or an extreme particle event, but because of an extraordinary absence. A silence in the sunspot record so deep, so prolonged, that it changed the climate of an entire hemisphere and left its fingerprints in the coldest winters Europe had experienced in centuries in the frozen Thames, in the failed harvests of the Little Ice Age, in paintings of frost fairs held on a river that no longer freezes at all. The sun went quiet, and the world felt it. For 70 years, the sun almost stopped making sunspots. Not completely, not permanently, but from approximately 1645 to 1715, a span of 7 decades covering the reign of Louis XIV in France, the English Civil War, the founding of the American colonies. The golden age of Dutch painting the sun entered a period of such profound quiet that some astronomers of the era spent entire careers watching the solar surface and seeing almost nothing. One of them, a Parisian astronomer named Jean Picard, recorded observing exactly one sunspot during an entire year of watching. One. In a year when, during a normal solar maximum, you might expect to see dozens of sunspot groups crowding the solar disk simultaneously. Another observer, the English astronomer John Flamsteed, the first astronomer royal appointed by King Charles II to improve navigational astronomy, noted in his records that sunspots had become so rare they were worth special comment when one appeared. In a period when a sunspot sighting was an event worth writing down, something fundamental had changed. This period is now called the Maunder Minimum, named after the British astronomer Edward Walter Maunder, who, in the 1890s, was the first person to systematically compile historical sunspot records and recognized that the late 17th century had been genuinely anomalous, not a gap in observation, not a failure of record-keeping, but a real and sustained suppression of solar activity, unlike anything in the surrounding centuries. And the world that lived through it felt something even if it had no language for the cause. The period overlapping with and surrounding the Maunder Minimum, roughly 1300 to 1850, though with regional and temporal variation, is known to climate historians as the Little Ice Age. This was not an ice age in the geological sense, not a period of advancing continental glaciers and mile-thick ice sheets. It was subtler than that, but in human terms, it was profound. Average temperatures across the northern hemisphere dropped by perhaps 1 to 2 degrees Celsius below the preceding medieval warm period. That sounds almost trivially small, but the difference between a comfortable climate and one that regularly fails, harvests, freezes rivers, and forces population relocations is often measured in fractions of a degree. Climate is a system of thresholds. Small average changes can produce large practical consequences when they push seasonal conditions past critical boundaries. The Thames froze, repeatedly reliably solidly enough to walk on, to hold markets to support the weight of oxen. The first frost fair on the Thames was recorded in 1607. By the Maunder Minimum, year's frost fairs had become almost a tradition, Londoners setting up booths and amusements on the frozen river, roasting meat over fires built on ice, printing souvenir pamphlets on printing presses dragged onto the surface. The last frost fair was held in 1814. The Thames has not frozen solidly enough to walk on since. In the Alps, glaciers advanced dramatically during the Little Ice Age, swallowing farms and villages that had been inhabited for centuries. Historical records from Swiss and French alpine communities describe the glaciers as moving entities with almost menacing intentionality. Communities petitioned bishops to come and formally blessed the glaciers, praying they would stop advancing toward their fields and homes. The Mer de Glace Glacier near Chamonix extended several kilometers further downslope than it does today. The retreat of alpine glaciers since the 19th century is not only a story of modern warming, it is partly a story of the Little Ice Age ending. In Iceland, sea ice extended much further south than in preceding centuries, disrupting the fishing routes that Icelandic communities depended on. In Scandinavia, the tree line moved downslope as growing seasons shortened. In colonial New England, the winters of the late 17th century were described by settlers in terms of hardship that modern Americans would find difficult to recognize as the same climate region. Now, here is where intellectual honesty requires careful navigation, because this is a topic where popular accounts frequently make a mistake that distorts the real science. The common telling of the Little Ice Age story goes something like this. The sun went quiet, the earth cooled, and the Maunder Minimum caused the Little Ice Age. It is a clean, satisfying narrative, and it is significantly oversimplified. The Little Ice Age began well before the Maunder Minimum. The cooling trend was underway from around 1300, more than 3 centuries before the sun went quiet. The causes were multiple and interacting. A series of large volcanic eruptions in the 13th and 14th centuries injected sulfur dioxide into the stratosphere, reflecting sunlight and triggering cooling that may have initiated a self-reinforcing cycle involving sea ice expansion and ocean circulation changes. Changes in land use across Europe and Asia, as populations were reduced by plague, allowed forests to regrow on agricultural land, changing regional albedo and carbon dynamics. The solar contribution to the Little Ice Age cooling is estimated by most researchers at somewhere between 0.1 and 0.3 degrees Celsius. Of cooling significant but only one voice among several in a complex chorus. This distinction matters enormously in the modern context, because the Maunder Minimum has been periodically invoked, sometimes by people acting in good faith, sometimes not, as a reason to be unconcerned about human-caused climate change. The argument runs, if the sun going quiet cooled the Earth in the 17th century, perhaps a new solar minimum could offset modern warming. The scientific community's response to this argument is clear and well supported. It cannot. Even the most optimistic estimates of solar forcing suggest that a new Maunder minimum would reduce global temperatures by perhaps 0.1 to 0.3 degrees Celsius over several decades, while current projections for human-caused warming over the same period range from 1 to 3 degrees Celsius or more. The sun dimming slightly would not cancel warming of that magnitude. It would be like turning down one burner on a stove while the oven is running at full heat. The Maunder Minimum is fascinating and important solar history. It is not a get-out-of-jail-free card for climate inaction. But let's stay with the Maunder Minimum itself, because beyond the climate debate, there is a deeper scientific mystery, one that touches the fundamental question of what drives solar cycles and what determines when they weaken. We do not fully understand what caused the Maunder Minimum. The 11-year solar cycle is thought to be driven by the differential rotation of the sun's plasma, the equator spinning faster than the poles, winding up magnetic field lines until they become unstable and break through the surface as sunspot pairs. This process should in principle be continuous. The differential rotation never stops. The physics that drive the cycle are always present. And yet somehow, for 70 years, the cycle was profoundly suppressed. Sunspots still appeared. Occasionally, the cycle didn't stop entirely, but activity was reduced to a fraction of its normal level. Something disrupted the amplification mechanism that normally takes the base dynamics and builds them into full solar maxima. Current research suggests the Maunder Minimum may be related to changes in the large-scale circulation of plasma in the sun's convection zone, the region just below the surface where hot plasma rises and cool plasma sinks. A weakening of the large-scale flows that transport magnetic flux from the equator toward the poles may have disrupted the feedback processes that normally amplify solar activity. But this is still an active area of research with competing models and unresolved debates. What we do know is that grand solar minima are not rare on the geological timescale. The The carbon-14 and beryllium-10 records we explored in the previous chapter show multiple extended quiet periods in the past 10,000 years, the Sporer minimum from roughly 1460 to 1550, the Wolf minimum around 1280 to 1350, and several others stretching back through the Holocene. They appear to occur roughly every 200 years or so, though not with the regularity of the 11-year cycle, which means the question of whether another grand minimum is coming is not purely hypothetical. In 2015, a researcher named Valentina Zharkova presented a model of solar cycle prediction at a meeting of the Royal Astronomical Society. Her model, based on two magnetic waves in different layers of the Sun's interior, predicted that solar cycles 25 and 26, roughly covering the 2020s and 2030s, would show significantly reduced activity, with cycle 26 potentially reaching Maunder minimum-like levels of suppression. The media response was immediate and enthusiastic. Headlines announced a mini ice age approaching. The story spread rapidly, combining genuine scientific uncertainty with the public's appetite for dramatic climate narratives. The scientific response was more measured. Several solar physicists pointed out that Zharkova's model was based on a limited data set, that its physical basis was not fully established, and that solar cycle prediction beyond 1 or 2 cycles is extremely difficult. Solar cycle 25, which began around 2019, has actually been more active than predicted by the model. Its rise toward maximum has been faster and stronger than anticipated, suggesting the Sun is not entering a quiet period, at least not yet. This is worth noting, not to dismiss Zharkova's work, but to illustrate something important. Solar cycle prediction is genuinely hard. The models are still evolving, and confident headlines about imminent mini ice ages, or conversely certain solar maxima, should be held with appropriate skepticism in both directions. Here is a question worth considering slowly: what would it actually mean for modern civilization if the Sun did enter a Maunder minimum level quiet period? The climate effect, as we've established, would be modest in the context of current warming trends. But there are other effects less discussed that might be more immediately noticeable. During solar minima, the reduced solar wind means the heliospheric magnetic field weakens, and that means more cosmic rays enter the solar system and reach Earth. Elevated cosmic ray flux has been linked in some studies to increased cloud nucleation and potentially to slightly increased radiation exposure at aviation altitudes. Satellite operators would actually appreciate the reduced atmospheric drag that comes with solar minimum. The reduced UV output would slightly reduce stratospheric ozone production. Most of these effects are small, but they are real, and they are a reminder that the Sun's variability touches systems we rarely think of as solar dependent. There is one more dimension of the Maunder minimum story that deserves attention, and it is perhaps the most human of all. The people who lived through it had no idea what was happening. The astronomers who recorded the absence of sunspots didn't know they were documenting a grand solar minimum. The concept didn't exist yet. They simply noted what they saw, or rather what they didn't see, and moved on to other observations. The farmers whose harvests failed the Londoners, who skated on the frozen Thames, the alpine villagers who watched the glaciers advance, they lived through the effects of a solar event of historical significance, without any awareness that the Sun was behaving unusually. Their explanations were theological, seasonal, local. The idea that the quiet surface of a star 93 million miles away might be influencing the length of their winters was not available to them. We are the first people in history who could in principle know. We have the data, the concepts, the instruments. If the Sun began a new grand minimum tomorrow, we would see it in our monitoring, data recognize it for what it was, and communicate it globally within hours. Whether we would respond wisely, whether governments and agricultural planners and infrastructure managers would adapt appropriately, is a different question. Knowledge does not automatically translate into action, but the potential for knowledge is itself something new under the sun, something worth appreciating quietly. The Maunder minimum shows us the Sun at its most passive, its most withdrawn a star pulling inward, dimming its magnetic voice, allowing the cold and the dark a little more room. And yet, even in that quiet, the sun was still present, still fundamental, still the source of every calorie of energy that kept those frost-fair revelers warm enough to stand on the frozen Thames and laugh. The sun's silence was never absolute. It was always still the center of everything. And speaking of centers of deep connections between the sun and the life it sustains, there is a dimension of this story we have not yet touched. One that is not about the sun's external behavior at all. One that is about what the sun has done over billions of years of evolution to the very bodies we inhabit. Because the sun has not only shaped our climate and our history, it has shaped our biology, our chemistry, the rhythms of our bodies, the architecture of our minds. We carry the sun inside us in ways that are only now beginning to be understood. Your body knows what time it is right now, not because you glanced at a clock, not because your phone told you. Your body knows at a cellular level, in the chemistry of your blood, in the firing patterns of neurons in a tiny region of your brain the size of a grain of rice, what time the sun is in the sky. Even here in the dark, listening to these quiet words, your biology is oriented toward the star that shaped it, running its ancient calculations, keeping its solar time. This is not metaphor. This is molecular biology, and the story of how scientists discovered it and what it reveals about the depth of the sun's imprint on living things is one of the most quietly astonishing chapters in modern science. We tend to think of the sun's influence on the body as simple and surface level. Sunlight warms us. Sunlight gives us vitamin D. Too much sunlight burns us. These things are true, and we will explore them with more care than they usually receive. But the sun's influence goes far deeper than skin. It reaches into the nucleus of nearly every cell in your body. It shapes the architecture of your brain. It governs the timing of your immune responses. It determines in ways researchers are still mapping your risk of certain diseases, your emotional baseline, and the quality of your sleep. We are not just organisms that live near a star. We are organisms that were built by one. Let's begin with the deepest level, the one that won the Nobel Prize. In 2017, the Nobel Prize in Physiology or Medicine was awarded to 3 American scientists, Jeffrey Hall, Michael Rosbash, and Michael Young. Their work, conducted over decades beginning in the 1980s, revealed the molecular machinery of the circadian clock, the biological timekeeping system that runs in virtually every living cell. The story begins surprisingly with fruit flies. Hall and Rosbash, working at Brandeis University, were studying a gene called period, already known to affect the timing of fly behavior, when they made a discovery that changed biology. They found that the protein encoded by the period gene accumulated in cells during the night and was broken down during the day in a self-regulating cycle of almost exactly 24 hours. The protein inhibited its own gene's activity as it built up. It slowed its own production, then as it broke down, production resumed. A molecular oscillator ticking away in cells, keeping time without any external input. Michael Young subsequently discovered additional components of this clockwork proteins called timeless and double time that fine-tune the cycle's precision. Together, the team worked out the basic molecular gear train of the biological clock, a feedback loop of proteins that rises and falls with the sun's daily cycle embedded in the genome of organisms that have been tracking solar time for hundreds of millions of years. The same basic clockwork, different genes, same logic operates in almost every living thing that has been examined. In mice, in humans, in plants, in fungi, in cyanobacteria that have been photosynthesizing for 3 billion years. The circadian clock is one of the oldest, most conserved systems in all of biology. Evolution found this solution very early and has kept it ever since. What this tells us about the sun is profound. The 24-hour day is not just a feature of Earth's rotation. It is written into the biology of life itself. Every living thing carries a shadow of the sun's rhythm inside it, a molecular echo of the rotating planet and its star ticking away in the dark. Now, here is the layer that most people have heard of, but rarely understood in its full depth. The primary way external light synchronizes the internal clock is through a pathway that was only fully described in the late 1990s, when researchers discovered a third type of photoreceptor in the human eye. Most people know about rods and cones, the light-sensitive cells responsible for vision in dim light and color, respectively. But in 2002, a researcher named Ignacio Provencio confirmed the existence of a third type intrinsically photosensitive retinal ganglion cells, or iPRGCs, which contain a photopigment called melanopsin. These cells are not involved in image formation at all. They do not help you see. Their entire purpose is to measure ambient light levels, specifically the intensity and spectral quality of light, particularly blue wavelengths around 480 nanometers, and report this information to a small region of the hypothalamus called the suprachiasmatic nucleus, or SCN. The SCN is the brain's master clock, a cluster of roughly 20,000 neurons that coordinates the timing of nearly every biological process in the body. When blue spectrum light, the kind present in abundance in natural daylight, particularly morning sunlight, hits the melanopsin cells, the signal travels to the SCN, which uses it to synchronize the body's internal clock to the actual time of day. This synchronization process is called entrainment. Without it, the internal clock drifts running slightly longer than 24 hours, for most people slowly falling out of sync with the solar day. The practical implications of this are familiar to anyone who has experienced jet lag. Jet lag is not simply tiredness from a long flight. It is the biological clock running at its previous time zone, while the external environment is running at a new one. Every system in the body, sleep hunger, hormone, secretion, cell division, immune, function core, temperature, is timed by the master clock and temporarily misaligned with the new day-night cycle. Recovery requires days of exposure to the new light cycle before the clock re-entrains. Shift workers experience a chronic version of this misalignment. Studies published in journals, including The Lancet Oncology and Journal of the National Cancer Institute, have found that long-term shift work sustained misalignment between the biological clock and the external light cycle is associated with increased risk of several health conditions, including cardiovascular disease, metabolic syndrome, and certain cancers. The World Health Organization classified night shift work as a probable carcinogen in 2007, based substantially on this evidence. The sun is not merely convenient for our sleep schedules. Misalignment from its rhythm sustained over years carries measurable health costs. But the sun's biological influence doesn't stop at the clock. Let's talk about vitamin D because this is one of the most widely discussed solar biological connections, and also one of the most widely misunderstood. Most people know that sunlight triggers vitamin D production in the skin. The common understanding goes, sunlight hits, skin vitamin D is made, it's good for bones. That's all true, but it's a small fraction of what vitamin D actually does. And understanding the fuller picture reveals something more interesting about the sun-body relationship. Vitamin D is not really a vitamin in the traditional sense. Vitamins are nutrients the body cannot synthesize and must obtain from food. Vitamin D can be synthesized by the body specifically when UVB radiation from sunlight strikes 7-dehydrocholesterol in the skin, converting it to a precursor that is then activated by the liver and kidneys. Because it is synthesized in the body and acts on distant target tissues through the bloodstream, vitamin D functions more like a hormone. And its receptor, the vitamin D receptor, or VDR, is found in the nucleus of cells in almost every tissue in the body. The immune system, the cardiovascular system, the nervous system, the endocrine system, muscle tissue, the gut. All of them have cells that respond to vitamin D signaling. The VDR, when activated by vitamin D, can influence the expression of somewhere between 200 and 2,000 genes, depending on the cell type and the research methodology used to count them. Vitamin D deficiency, which is remarkably common, affecting an estimated 40 to 50% of adults in the United States, and higher proportions in northern latitudes and among people who spend little time outdoors, has been associated in epidemiological studies with increased risk of autoimmune conditions, cardiovascular disease, depression, cognitive decline, and complications from infectious diseases, including influenza and COVID-19. The connection between latitude sunlight availability and health outcomes has been observed for decades. People living at higher latitudes further from the equator receiving less intense solar UVB radiation, particularly in winter, show systematically different patterns in multiple health metrics compared to people at lower latitudes. Multiple sclerosis prevalence, for example, increases dramatically with distance from the equator in both hemispheres. A gradient so consistent, it was one of the early clues that solar exposure might play a role in immune regulation. Here is something that reframes all of this in a way I find quietly powerful for virtually the entire history of the human species, the entire 300,000 plus years of Homo sapiens. Humans lived outdoors in natural light, sleeping when dark and waking with the dawn. The vitamin D levels maintained by traditional outdoor lifestyles were far higher than those typical of modern indoor dwelling populations. The circadian clock was entrained daily by direct exposure to morning sunlight. The body's solar relationships were continuously naturally maintained. The modern indoor life, this specific historically unprecedented way of living, has decoupled human biology from the sun in ways that are only now being fully mapped. We moved indoors behind glass that blocks UVB under artificial lights that lack the blue wavelength intensity of sunlight on schedules determined by clocks and work demands, rather than by the rising and setting of our star. And the biological systems that evolved over millions of years, assuming a particular relationship with the sun, found themselves in a novel environment they were not designed for. This is not a call to guilt or anxiety. It is worth naming clearly because it contextualizes the epidemics of vitamin D, deficiency sleep disruption, circadian misalignment, and perhaps some of the mental health challenges of modern life in a way that has actionable implications. Not everything about modern indoor life is fixable by more sunlight, but some meaningful portion of it may be. Speaking of mental health, let's talk about something that is both well-established and still underappreciated: the sun's direct effect on mood and brain chemistry. Serotonin, often described as a neurotransmitter associated with mood stability and well-being, is produced in the brain and in the gut in quantities that are directly influenced by light exposure. Multiple studies have found that serotonin turnover in the brain, how quickly serotonin is synthesized and used, is higher on bright sunny days and lower on dark overcast ones regardless of season. The effect is driven not by warmth, but by light intensity reaching the eyes. Seasonal affective disorder, or SAID, affects an estimated 1 to 2% of the U.S. population in its full form, with a milder version called subsyndromal SAD, affecting perhaps 10 to 20%. It is most prevalent at higher latitudes and is characterized by depressive symptoms that emerge in autumn and winter as day length shortens and light intensity decreases. The first-line treatment light therapy using bright full-spectrum light boxes that simulate intense daylight is effective for the majority of patients. You are in essence giving the brain the solar signal it evolved expecting to receive. There is a question worth pausing on here, one that feels both personal and vast. How much of the ordinary variation in human mood, the subtle difference between a bright spring morning and a gray November afternoon, between a week of sunshine and a week of overcast skies, is the sun directly adjusting the chemistry of your brain? The answer suggested by the research is more than most people intuit. The sun is not just illuminating your world. It is through pathways that evolution built over hundreds of millions of years, actively participating in the biochemistry of how you feel. Melatonin completes the circuit. Where serotonin rises with light, melatonin, the hormone that signals darkness and promotes sleep, is suppressed by light and released in the absence of it. The pineal gland, a small structure deep in the brain that Descartes once called the seat of the soul, begins producing melatonin in the evening as light levels fall, preparing the body for sleep. It is suppressed during the day by the light signals reaching the SCN from the melanopsin cells in the eye. The whole system, melanopsin cells, detecting light SCN, synchronizing the master clock, serotonin rising with the day, melatonin rising with the night, is a biological instrument tuned over hundreds of millions of years to the rhythm of a single star. It is, in a sense, a solar radio receiver. Your body is always listening for the sun, even when you are not. And here, perhaps, is the most unexpected implication of all this research, the one that tends to land differently when stated plainly. The sun's influence on human biology is not passive. It is not the case that the sun happens to provide useful light and warmth that humans have learned to exploit. The relationship is older and more intimate than that. The sun shaped the evolution of the molecular machinery that runs your body's timing. It drove the selection of the photoreceptors in your eyes that detect not just images, but meaning, time of day, season orientation in the solar cycle. It calibrated the neurochemical systems that regulate your mood, your alertness, your immune function, your sleep. Every morning, when light enters your eyes and reaches those melanopsin cells and travels up the optic nerve to your hypothalamus, it is completing a circuit that was built over hundreds of millions of years of evolution under this specific star. The sun is not just outside you. It is in a measurable molecular sense encoded inside you. We carry the memory of every sunrise our ancestors ever lived through, written in chemistry and protein, and the slow logic of natural selection. And if the sun has written itself so deeply into the biology of living things, into the molecular clockwork of cells, into the architecture of the brain, into the chemistry of mood and sleep and immunity, then perhaps it should not surprise us that its ultimate fate, the story of what this star will eventually become, feels not just astronomically significant, but strangely personal. Because the sun's future is in the most literal sense possible our future too. And that story of a star in the second half of its life, slowly brightening, slowly swelling, moving toward an ending that is billions of years away, and yet already in some small ways already underway, that is where we go next. There is a number that cosmologists use when they want to put human civilization in perspective. The sun has been burning for approximately 4.6 billion years. It has enough hydrogen fuel remaining in its core to continue burning for approximately another 5 billion years. By the standards of the universe, our star is middle-aged, settled, reliable. In the comfortable, productive phase of its life, where it shows up every morning, does its job, and goes down every evening without drama. But middle age, even for stars, does not last forever. And the story of what happens to the sun, not in some abstract cosmological future, but in time scales that touch the actual question of life on Earth, is both more imminent and more nuanced than most people realize. Because the sun is not static even now. It is slowly, imperceptibly, continuously changing, and some of those changes have already begun. Right now, as you listen, the sun is about 30% more luminous than it was when Earth formed 4.6 billion years ago. The sun brightens by roughly 1% every 100 million years as helium accumulates in its core and the core gradually contracts and heats. 1% per 100 million years sounds negligibly slow, but over geological time, it adds up to something significant. And it poses one of the most fascinating puzzles in planetary science. The puzzle is called the faint young sun paradox, and it was first clearly articulated by Carl Sagan and George Mullen in 1972. The problem is this: if you run the sun's luminosity backward in time, the young sun 3 to 4 billion years ago was 20 to 30% dimmer than today. Standard climate models suggest that with a sun that faint early Earth should have been completely frozen, a solid ball of ice, uninhabitable, incapable of supporting the liquid water that geological evidence clearly shows was present in abundance by at least 3.5 billion years ago. Early Earth was not frozen. Life appeared. Liquid oceans existed. Something kept the planet warm enough, despite a significantly dimmer sun. The leading explanation involves greenhouse gases, particularly carbon dioxide and methane, present in the early atmosphere, at concentrations far higher than today, trapping enough heat to compensate for the reduced solar output. There is also evidence that early Earth may have had different ocean chemistry, different cloud cover, different albedo. The solution is probably a combination of factors, and researchers are still working out the proportions. But here is what the paradox reveals. Earth's climate is not a passive recipient of solar energy. It is an active responsive system that has over billions of years adjusted its greenhouse composition to maintain roughly habitable conditions despite a steadily brightening star. The atmosphere, the oceans, the carbon cycle, the biosphere, all of them interact in feedback loops that have helped stabilize the planet's temperature across an enormous range of solar output. This is in a sense deeply reassuring. Earth has a history of adapting to solar change on geological timescales. But it is also, in another sense, sobering, because that adaptive capacity has limits, and the sun is going to push those limits eventually. In approximately 1 billion years, not 5 billion, not when the sun becomes a red giant, but in 1 billion years, a time scale that is shorter than the current age of complex animal life on Earth, the sun will be bright enough that even the most optimistic climate feedback mechanisms may not be able to prevent a runaway greenhouse effect. As solar output continues to increase, the oceans will warm, evaporation will increase water, vapor will accumulate in the atmosphere as an additional greenhouse gas, which will cause more warming, which will cause more evaporation. A self-amplifying cycle that once fully initiated leads to the loss of the oceans to space. The process by which this happens, photodissociation of water vapor in the upper atmosphere by solar UV radiation, followed by hydrogen escape to space, is the same process that stripped Venus of its water billions of years ago. Venus and Earth formed at roughly similar distances from the Sun from similar material. The divergence in their fates is, researchers believe, at least partly a story about Venus receiving slightly more solar energy, crossing the threshold into a runaway greenhouse earlier, and losing its water before it could be incorporated into a stabilizing carbon cycle. Earth is in some respects a luckier Venus, a cooler Venus, a Venus that got to keep its oceans long enough for life to emerge and flourish for billions of years. That luck has an expiration date measured in geological time. Now, let's follow the sun's own trajectory further, because what happens to the star itself is a story with its own quiet drama. As the sun continues to fuse hydrogen in its core, the helium ash accumulates. The core contracts under gravity, heats up, and the surrounding shell of hydrogen burns faster. The sun's outer layers expand in response. This process, gradual at first, then accelerating, will eventually transform the sun from a yellow dwarf into what astronomers call a red giant. In approximately 5 billion years, the sun will have expanded to perhaps 100 to 200 times its current radius. At that size, it will engulf Mercury. It will engulf Venus. Whether it engulfs Earth is a question that has a surprisingly uncertain answer. The expansion will cause the sun to lose significant mass through an intensified solar wind. And as the sun loses mass, Earth's orbit will spiral outward, potentially just enough to stay ahead of the expanding surface. Potentially. The most recent detailed models suggest Earth's orbit will expand, but probably not fast enough. Earth will likely be engulfed, or at minimum have its surface completely vaporized by the extreme heat of a sun radiating thousands of times its current luminosity from an envelope extending nearly to Earth's current orbit. But Here is something that reframes this in a way I find unexpectedly beautiful. Long before the red giant phase, long before Earth is engulfed, the sun will have become too bright for liquid water to persist on Earth's surface. Life as we know it will not survive that transition. If there are descendants of Earth's biosphere alive in 1 billion years, whether biological, technological, or something we cannot currently imagine, they will have needed to find other homes, other stars, other worlds at the right distances from their own suns. The sun's biography, in other words, contains within it the ultimate argument for why life, if it is to persist, must eventually become interstellar, not as a choice, as a necessity written in stellar physics. Carl Sagan expressed something close to this when he wrote in Pale Blue Dot that the Earth is a lonely speck in the great enveloping cosmic dark, and that our obligation to survive and flourish requires us to become eventually a spacefaring species. He was making a philosophical argument, but the astrophysics underneath it is precise and measurable. The sun's clock is running. Life has approximately 1 billion years of comfortable habitability remaining on Earth, and perhaps another few 100 million years of marginal habitability beyond that. That is, to be clear, an almost incomprehensibly long time by human standards. Anatomically modern humans have existed for roughly 300,000 years. A billion years is 3,000 times longer than our entire species' history. There is no reason for urgency not on this specific timescale, but there is something worth sitting with quietly in the dark. We exist now, in this particular window, in this specific 4.6 billion year moment in the sun's 10 billion year life. We are not at the beginning, the wild volcanic barely formed beginning when life was first finding its footing in hydrothermal vents. We are not at the end, the brightening, expanding, increasingly hostile end that will come in geological future. We are in the middle, in the stable, temperate, comfortable, extraordinarily improbable middle. Astronomers have a term for this, the habitable zone, or sometimes the Goldilocks zone, the range of distances from a star where liquid water can persist on a planet's surface. Earth sits squarely in the sun's habitable zone right now. But the habitable zone is not fixed. It moves outward as the sun brightens, and Earth has been tracking the inner edge of that zone for billions of years, fortunate to have formed far enough out, with enough atmospheric regulation to remain habitable as the zone shifted. We live on a planet that has been threading a needle for 4 billion years. Here is a question to hold gently, not with anxiety, but with genuine wonder. What are the odds? What are the odds of the right star, the right planet, the right distance, the right atmospheric composition, the right magnetic field, the right moon, stabilizing the axial tilt, the right timing within the star's life cycle, all of it coming together in exactly the combination that allows not just life, but complex, conscious, curious life, life that can look back at the star that made it and ask, what are you really? What are you doing to us? What will you become? We don't have a complete answer to the odds. Question the Drake equation attempts it, and astronomers argue productively about its terms. The James Webb Space Telescope is right now taking spectra of exoplanet atmospheres looking for the chemical signatures of life around other stars. We may, within the lifetimes of some of the people listening to this, have our first tentative evidence of biology beyond Earth. If we find it, or rather when we find it, if the distribution of life in the universe is anything like the distribution of habitable planets we are beginning to map, it will be life built by its own star, shaped by its own star, carrying its own star's rhythm in its own molecular clockwork. Life tuned to a different frequency, solving the same problems: energy timing, temperature regulation, protection from radiation, with different chemistry under different light in the shadow of a different sun. The sun is not unique in what it does. There are an estimated 200 to 400 billion stars in the Milky Way alone. Of those, perhaps 20 to 40 billion are G-type or K-type stars similar in size and temperature to our sun, with planets in their habitable zones. The physics that drive sunspots and solar flares and coronal mass ejections operate on other stars too. Stellar weather is not a solar peculiarity. It is a feature of stars. What is particular to our sun is its relationship with us, the specific way its light calibrated our circadian clocks, the specific way its particles carved the shape of our magnetosphere over billions of years, the specific way its brightening history drove the evolution of Earth's carbon cycle, and through it, the rise and fall of life's great chapters, the specific way its quiet dark side, all those hidden forces we've been exploring tonight, shaped human history in ways that went unrecognized for millennia. When the Parker Solar Probe makes its closest pass of the sun, skimming through the corona at 430,000 miles per hour, closer to the sun's surface than any human-made object has ever traveled, protected by a carbon composite heat shield, facing temperatures of nearly 2,500 degrees Fahrenheit, it is in one sense doing something purely scientific. Measuring magnetic fields, particle velocities, wave phenomena in the corona data that will improve space weather models and help protect satellites and power grids. But in another sense, it is doing something that feels almost ceremonial. Humanity born from a star's energy, evolved by a star's light, sustained by a star's warmth, sending a small piece of itself back toward the source. Getting as close as physics and engineering currently allow. Listening, asking, what are you really? The answer after everything we've explored tonight is something like this. The sun is a nuclear furnace converting 600 million tons of hydrogen into helium every second, and has been doing so for 4.6 billion years. It is a magnetic weather system of extraordinary complexity, cycling through 11-year rhythms of storm and quiet, occasionally erupting with energies that dwarf all of human civilization's total energy output. It is the architect of Earth's magnetosphere through the solar wind that shapes it. It is the author of auroras and the destroyer of satellites. It is the source of every calorie of food you have ever eaten through the chain of photosynthesis. It is the keeper of your body's clock through mechanisms built into your cells over hundreds of millions of years of evolution. It is the sculptor of Mars's barren surface through the atmospheric stripping that took that planet's oceans. It is the timekeeper of Earth's deep history written in the carbon-14 of ancient trees and the beryllium-10 of polar ice. It is quietly the most important object in human existence. And we spent most of that existence looking at it and seeing only light. Tonight I hope you see a little more. We have traveled from the first moments of Galileo's sunspot sketches to the molecular clockwork in your cells, from the ancient frozen Thames to the future engulfed Earth, from Richard Carrington watching a white flash on the solar surface to the Parker Solar Probe diving into the corona at 500,000 miles per hour. From the patient chemistry of a 9,500-year-old tree to the question of whether life somewhere around another star is right now listening to its own sun's quiet processes and wondering as we are what it all means. The sun's dark side is not really dark. It is simply the side we were not looking at, the side that operates in wavelengths we cannot see in timescales that exceed human memory, in forces too large and too subtle for unaided human perception. The side that acts on us, constantly shaping us, protecting us, occasionally threatening us, always sustaining us without asking for acknowledgement and without requiring that we understand. But understanding, it turns out, is its own kind of gift. Thank you for spending this night with the sun. Thank you for listening with the patience that quiet science deserves. Thank you for letting curiosity do the listening while the rest of you rests. If this journey moved something in you, if you found yourself sitting a little differently in the light of what the sun actually is, I'd love for you to leave a comment below. Tell me what surprised you most. Was it the Carrington event? The Miyake spike hidden in ancient tree rings? The molecular clock in your cells tuned to a star? The idea that we live inside the sun's own breath? And if you'd like to continue these quiet journeys through the science that surrounds us without announcing itself, through the hidden mechanics of the world we think we know, subscribe if you haven't already, and stay close. There are more stories waiting in the dark, stories about the deep ocean that covers more of Earth than we've ever mapped, Stories about the strange physics of time and why it flows only one direction. Stories about the invisible forces threading through every living thing on this planet and the ones beyond it. The universe has more to whisper, and we have all the time in the world to listen. Sleep well, friends, dream gently, and the next time you step outside into the morning light and feel the warmth on your face, remember that it took 170,000 years to reach the sun's surface, 8 minutes to cross 93 million miles of empty space, and your entire evolutionary history to build the body that receives it. Good night.